Okay, so first up, we're going to have Aaron Allen. This is the second session, by the way, Haskell Implementers Workshop. Welcome. Hope you all had a good lunch. Aaron Allen is going to be telling us about a GHC plugin for setting breakpoints. So thank you, Aaron.
Thanks, Ben. Yeah, so my name's Aaron Allen. I work for a company called HIW'23, which is a popular supermarket chain in Texas, and some of our back-end services are written in Haskell. So I'm on the industrial side of things. And today I want to present a GHC plugin that I wrote to implement some breakpoint functionality. I found that having developer tooling facilitated by a plugin is sort of a sweet spot in the ecosystem for using plugins because you're not depending on it so much as far as your production code goes. So you can drop that dependency if the plugin is no longer maintained or something like that. So why make a plugin for breakpoints? So as you may know, there's a debugger built into GHCi that has presumably the ability to set breakpoints, but I've encountered a number of bugs with it, especially when it comes to concurrent programs like a web server. And I'll go ahead and demonstrate what I'm talking about with that. So here I have a simple program that's using concurrency to just fork a thread.
Can you make the text bigger?
Yes. So I'm just forking a thread here, and then I have a loop running in the main thread. So I will load this in GHCi, and I'm going to set a breakpoint on this line 13, and then I'll run the program. Okay, so a few things to notice here. The main thread is still running, even though I'm supposedly at a breakpoint. And also it didn't display this variable that I have bound. So that's missing, like it should be here alongside this result binding. And then furthermore, if I try to terminate this program, so I press Control-C once, nothing happens. If I press Control-C again, well, nothing happened again. Yeah, so right now it's in a bugged out state where I'm at the GHCi. Well, hang on. Actually, I need to continue. That's what I forgot to do. Okay, so now I've released the breakpoint, and now if I Control-C, I have to Control-C twice to get back to the GHCi prompt. However, the main thread is still running in the background. And the only way I found to kill it is to restart GHCi. And that's unfortunate because then I have to reload all my code as bytecode. And if you're working with a large application, that's a pain. And I can't just like re-execute the program like I can in this case because I'm not running a web server. But if I were running a web server, the port would be bound already, so I would be out of luck there. So in this case, I just have to quit and restart GHCi. So yeah, that's the main issues that I have with the built-in debugger. So what can we get with the plugin approach? Well, we don't have this issue with concurrency. And furthermore, I can pause execution of the program across all threads. And not having a reliance on the bytecode interpreter is nice because I don't have to load everything in as bytecode. If I'm testing something that involves multiple executables interacting in a concurrent way, I can compile a breakpoint into an executable and just run it without having multiple GHCIs running and using up a ton of memory. Also, your breakpoints are declared explicitly in the code rather than the sort of command line interface that GHCi has. So let's look at what that does. So I'll use this function called breakpoint IO and just insert that into my code. I will also turn on the plugin by passing this flag to GHC. So now if I run the program, so I get this output that says that I've hit a breakpoint. It gives you the location of the breakpoint, and then you'll get a list of all the bindings that are in scope at that point. And if you'll notice, the main thread isn't running in the background like it was before. It's actually stopped. So then after I press enter, execution continues as expected. Right, so the API for this plugin is pretty similar to debug.trace. If you're someone who uses tracing to debug your programs using the debug.trace module, this API is pretty similar in that you get these different variants of the functions. So I have breakpoint IO that is geared towards a monad with a monad IO instance. And you should use breakpoint IO if at all possible, because it doesn't rely on unsafe perform IO at all. So there's no lazy IO thunks flying around. But there's also just the regular breakpoint function, which is a pure function that takes an argument. And there's also breakpoint M, which is for a monad that does not have a monad IO instance. And then there's another variant called query bars. So with this, instead of seeing, okay, so this behaves rather differently than breakpoint, the breakpoint function. In this case, it doesn't halt the execution of the program. It's just using a naive sort of waiting for standard in blocking on this thread. So in this case, I still see the main thread running, but what I do have is a prompt where I can enter variable names, and then I'll get this output. And the string is, in this case, it's generated lazily. So if you have a program where it's entering an infinite loop somehow where you've, say, bound a variable to itself, you can, it's helpful to identify that case, because I can evaluate that specific variable and see, like, okay, this is the variable where that's happening, rather than sort of blindly guessing. So yeah, query bars gives you that prompt, but you don't have some of the more magical features like pausing the runtime or some other things that I'm going to mention soon. There's also this exclude vars function where I can pass in a string containing the identifier that I don't want to appear in the output. So now I don't get any bindings for the breakpoint. Okay, moving on. So there's actually two different components to the plugin. It's both a renamer plugin as well as a type checker plugin. And the renamer portion of the plugin, it goes through and traverses the Haskell expression tree that results from renaming. And in so doing, it collects up identifiers and makes sure that they're scoped correctly. And whenever it encounters one of these API function calls, it replaces that with code which has access to a map containing all of those bindings in it. So that's how I'm able to display those bindings to the user. I'll show you what that code looks like. So it's a huge pain to do case analysis on the Haskell expression tree itself, because it's so massive. but it has a data instance that allows you to do some data generic traversal of it. So that's what I'm doing here. Like I have a case for each constructor that I'm interested in, and then I'm using the alternative instance of maybe t to try each of these cases. And I'm doing a top-down traversal so that I'm collecting variables up from the outermost scope and pushing them into the innermost scope. And the monad that I'm doing this in is based on reader T, which is really well suited to maintaining the scoping of variables in this case. And there's some interesting like quirks you have to be aware of. So like for a let binding, for example, like in the source code, you can put them in any order you'd like. However, after the renamer, they're ordered in such a way that any dependency between those let bindings is reflected in the order that they get put in the renamer output. So what I have to do is do a sort of dependency analysis on those and potentially put them in a different order based on whether a breakpoint expression appears in one of those bindings and it therefore references the other let bindings, thereby changing its dependency ordering. And I'm doing that by actually vendoring a function out of GHC, which is not exposed by the API, but it just goes and does a sort of graph analysis and identifies the strongly connected components in order to group those let bindings correctly. Yeah, but that's pretty much the renamer portion. So the other side of the plugin is the type checker plugin, and its purpose is to allow you to display any value regardless of if it has a show instance or not. And also, even if it's a unlifted value. So the mechanic behind this is that I have this type class. Actually, it's in. I have a type class called showLev, which is very similar to show, except it's levity polymorphic. And that just allows me to handle this case where I want to show unboxed types. So I have handwritten instances for an assortment of unboxed types. There's also code within the plugin to deal with unboxed types that I don't have instances for. So if we go ahead and look at that, sorry. Okay, so the main thing that's happening here is that I'm given a list of wanted constraints, and then what I want to do is check if any of those are for this showLev type class. And I have a special case for if it's an unlifted type, but in the lifted type case, I'm going to then want to have a show dictionary for that type. So in this showLevDict function, I'm making a new wanted constraint for the show class, and then I'm using that dictionary to pass into what I'm trying to build in order to satisfy the showLev constraint. And there's more to it than that, because if you have a type which, the outermost constructor does have a show instance, but then you have inner parts that don't have a show instance, then I want to show that outer part, but then default to a kind of phony dictionary for the inner type. And all the phony dictionary does is it just shows it prints the type of that value. And the way that I'm able to identify that that's the case is that if I get a wanted constraint for the show type class, I can inspect its provenance via the CT origin type. So occurrence of is a constructor of that type. And this happens whenever GHC emits a constraint due to a use of some class method. So like in this case, it would be the showlev method of the showlev type class. And then I can check that the name here is that showlev name. And if it is, then I can say that, oh, this show constraint originates from a use of showlev, in which case I want to emit a phony dictionary. And just to sort of demonstrate what that looks like. So if I remove this deriving show, so here I just get the name of the type, which is record, within angle brackets. And if I put it in a list, then that constructor also gets printed using its show instance. So the other aspect to this is the ability to pause the execution of the program. And there's a number of ways to do this. The way that I'm doing it currently is a little bit of a hack. So if you have a foreign function call which is marked unsafe, then the runtime will block until that call returns. And so I can kind of abuse that mechanic. So here I'm using the GHC function as an unsafe foreign function call, and that effectively blocks the runtime system awaiting input from the user. And interestingly, this didn't work prior to 9.2. Well, it did, however, while you were examining your breakpoint output, your computer would get really toasty because the CPU would be at max utilization. I don't know why, but it got fixed in 9.2, thankfully. So if it's not 9.2, then I just resort to this naive use of getLine. What I would like to do is use the RTS API to use the actual function that pauses the RTS, which GHC debug uses. But I've run into issues with my CI runners for Windows, specifically using that. So I've just been sticking with the old git char unsafe foreign function call for now. There's also this point about pausing timeouts. So if you're using thread delay, then the way that that's actually implemented is there's a priority queue that picks off callbacks for thread delays that are keyed at a certain point in time. And if you set a breakpoint and then release the breakpoint after a certain point, then those callbacks will all fire at once if enough time has elapsed. So what I'd like to be able to do is pause those timeouts somehow. And the way that I'm doing that is to actually manipulate that priority search queue, which is not exported by GHC. So to bring it into scope, I have to use the magic of template Haskell to break down the module barrier. So in here, what I do is, when I hit a breakpoint, I add a year to all of the entries in the priority search queue. So if you were blocked for more than a year, then it wouldn't work. But then after the breakpoint is released, I just subtract 1 year minus the amount of time that's elapsed. And I realized that this would break for 32-bit systems because they can only represent like 30 minutes worth of nanoseconds or whatever this is. But yeah, that's how I stop timeouts. What happened here? Okay. Yeah, so you can easily shoot yourself in the foot if you have more than one breakpoint that's referencing each other. That will result in an infinite program. And I've made it such that a binding doesn't have itself in scope, even though it technically is in scope. And that's just so, that foot gun is somewhat tamped down. But you do have to be careful with this. And that's where the exclude vars function can be useful if you are setting more than one breakpoint that are within each other's scopes. You can also have issues with polymorphic local bindings, like some where binding that's just a do statement without any type signature. It'll raise type errors about not having whatever, like monad IO instance. So you can solve that by either giving a type signature or using mono-local binds. Some ideas I have for developing this a bit further would be have a separate UI process, sort of like GHC debug brick, the brick interface that GHC debug has, so that you can more effectively use this with like brick-based applications that take control of the terminal, and furthermore utilizing the RTS API more to do some sort of heap analysis. All right, that's all I have.
Excellent. All right. Yes, all right. Uh-oh. Get the hole a little bit to turn it on. There we go. Okay. Yes, thank you, Aaron. I think we had a question from Etzko over here.
Thanks. You're a brave man. I have a question and a comment. A comment is, I have a package called recover_rtti, which exports a function anything to string. Might be useful for you. It actually would be able to print your record, for example, even if there's no show instance. Might be useful. Question is, can you have conditional breakpoints?
Yeah, so I could, since it's just regular Haskell code, I could put it in like a when function call or some other control flow structure.
Right, but I typically might want to have, like, I'm not really sure where my code is breaking. I might need a whole bunch of breakpoints and then just sort of like in GHCi or some other way manipulate which ones I want to enable or disable.
Oh, no, that's not built in. But yeah, that's an idea that could possibly be implemented. And also I have tried that recover RTTI package, and I ran into an issue where when I tried to print a value, I think it was the vault type, like in a servant endpoint, it segfaulted. So I kind of backed off of that.
I mean, it does evil stuff. So.
Yeah.
It seems like there are really two ideas here. There's the breakpoint idea, and then there's the show anything idea. And they might actually be beneficial as distinct packages, even. If you can't.
Yeah, that's a good point.
All right. I'm afraid that's all we have time for comment-wise or question-wise. So let's have it again for a speaker. Welcome our next speaker.